All right. Welcome everybody to another physics lecture. Today we are going to be talking about Newton's first law of motion. All right. Okay. So let's just jump right into this. All right. Sir Isaac Newton is one of the most important physicists that has ever lived, and one of the reasons why he is so important to science and just the world that we have around us right now is that he came up with these three laws of motion that we're going to be looking at. The first one is his law of inertia, which is a word I'm sure that you've heard before, okay? And I bet that you've heard these words somewhere in your life. But Newton's first law says the following: an object that is in motion stays in motion, and an object that is at rest stays at rest. The bit that you might not hear is this last part: unless acted on by an unbalanced force. And this idea of forces is what we're going to be introducing today. So the main focus today is going to be the idea of balanced forces versus unbalanced forces, what they look like, what causes them, and how they affect the world. Okay? So as you're watching, be sure to copy down the important information in your notes. This right here, super important. Definitely write this down. Okay? All right, so as you're doing that, you can look at this video here of this car and this unfortunate gentleman flying out of it, all right? This is a real life occurrence. This is what happens when you don't wear a seatbelt, right? If you don't wear a seatbelt and you hit something, okay, you keep going forward. Why? Okay, because of inertia, all right? So as it says, an object in motion stays in motion, okay? Well, look at this. As you're moving, you are moving along with the car, right? You and the Lambo are both moving. If you hit a wall, okay, that wall is what we call an unbalanced force. It's a force that stops the car, okay? But you're not tied down to the car. So when you hit the wall, you stay in motion, right? You keep moving forward because you are in motion, all right? The reason we invented seatbelts is so that they can be the unbalanced force that acts upon us, that keeps us steady and in place, all right? So let's look at balanced forces first. This is easier, right? Balanced, as I'm sure you know, means that two things are equal, right? Okay, balanced forces are two things, and again, write this down. They're equal in size, right? They're the same size, or what we call magnitude, meaning the number's the same, and they're opposite in direction. Balanced forces do not cause a change in motion, all right? Now this phrase, change in motion, you could also think of this as change in velocity, meaning they don't cause any acceleration, all right? There is no acceleration happening with balanced forces, okay? If a force is balanced, okay, that means that the object can either be at rest, which is what you usually think of it as a balanced force, right? The object is at rest, but the object can also be at a constant velocity, right? Now let's think about that. Here we can see some pictures. Right? The next thing we see here is the net force on the object, okay? And if you've never seen this word net before, the word net simply means total, okay? Net force on the object equals 0 newtons. Newtons is what we measure force with. So you're gonna hear that word a lot today, but newtons measure force. Okay, so here we have two scenarios, okay? Forces can either be pulls or pushes, all right? Okay. In both of these instances, okay, we have a tug of war stalemate and a arm wrestling stalemate. What's happening is we have two forces, red and blue, okay, that are equal in size, right? The magnitude is the same, but they're opposite in direction. So what does this cause? This means that these two guys are going to stay at rest, okay? Same thing with the tug of war, but instead of a pull, it's a push, okay? But those two forces are pushing with the same amount of newtons in size, but they're going opposite directions, right? So both of these are what we call balanced forces. Okay, that's pretty easy. Now again, I want to go back to this. Most of the time, we see a balanced force as something that is at rest. That makes the most sense. If it's not moving, okay, it's not in motion, it's balanced. Yes. But we need to understand that if an object is at a constant velocity, okay, meaning it's moving in a straight line at the same velocity, that is also a balanced force, okay? And the reason is because if there's a constant velocity, if you're moving in a straight line at the same speed, there's no change in your motion. And you've probably felt this. If you've ever been on a train or an airplane or a bus that's moving in a straight line, okay, if it doesn't change speeds or turn, it's almost like you're in a stationary room, okay? It's not until the train speeds up or slows down or turns that you feel any kind of force moving you, all right? So forces, and this is something that I'm going to keep saying, forces are acceleration. If the forces are balanced, there is no acceleration, all right? Okay, and again, that means you're either at rest or a constant velocity. Okay, so take a second here. Let me erase this. I want you to read these examples. Which one of these is an example of a balanced force? Read through them. A bicycle making a turn, a rocket accelerating into space, a car moving at a constant velocity, or a spinning top. You got your answer? 3, 2, 1. Did you say the car moving at the constant velocity? If you did, very good. Okay, this is a balanced force. That car is moving straight at a constant velocity, all right? You don't feel any forces, okay? The bicycle turning is changing direction. That's acceleration. The rocket accelerating is accelerating, and the top spinning is also changing direction. So all three of these are all balanced forces. A train moving in a straight line at a constant speed, okay? Two equally sized things on a scale, or just a little kitten at rest. So an unbalanced force, these are the ones that we talk about more often. What is an unbalanced force? Oh, these all come all at once, I'm sorry. All right. Unbalanced forces always cause a change in motion, or really what is called a change in velocity, okay? They are always accelerating. Unbalanced forces are always accelerating. Their velocity is always changing, okay? Which means they can either be changing their speed, they can be speeding up or slowing down, or they can be changing their direction, okay? And the net force, whatever it is not zero. So balanced forces, your total force is equal to zero because they're equal in size and opposite in direction. Balanced forces, there is a number, whether it's 1, -1, a million, whatever it is, there is a net force. So for instance, in this case, here we have two gentlemen kicking a soccer ball. This one is kicking with 75 newtons. This one is kicking with 125 newtons. All right. Now, the nice thing about forces is that they're easy to figure out. Okay, figuring out what's called a net force is very easy. If the right is kicking 75 newtons and the left is kicking 125 newtons, what do you think we do to these forces? Well, they're going in opposite directions, so we subtract them. 125 minus 75 gives me a total of 50 newtons, and then you just got to see which one's bigger. Well, the blue one's bigger. So what's our total force? The total force is going to be going to the left at 50 newtons. Pretty straightforward. Okay? Finding total forces is not terribly difficult, which is good for today. In fact, I think most of what we're studying today is pretty straightforward. So let's look at some examples. All right. Here, we're going to have two forces. Just looking at the picture, you can tell that they're unbalanced. Look, blue's bigger than red, right? So if we put numbers to this, let's say the red is 3 newtons. Let's say the right is 6 newtons. Again, they're going in opposite directions, so we subtract. That gives us 3 total newtons. Left was bigger, so we have 3 newtons going to the left. Pretty easy. Here, do these look balanced or unbalanced to you? They look pretty unbalanced to me, right? Now we're pulling, right? Red is pulling to the right, or sorry, to the left. Blue is pulling to the right. Just with even out numbers, I can see blue is bigger. So I know that this guy's gonna win. I know he's green. I didn't color coordinate it great. So if the red arrow is 4 newtons and the blue arrow is 10 newtons, okay, red's going right, blue's going left, what's our total force gonna be here? Think about this. Well, you take 10 minus 4, and you should have said 6 newtons. Going to the right. This guy's gonna win, right? If you got more force in tug of war, you win. That's it. Okay, now here, instead of having them fight against each other, now we have them helping each other out. If red and blue push in the same direction, guess what? We're not going to subtract their forces. We're going to add them. If red is 5 and blue is 10, 5 plus 10 gives me my total force, which is 15. Because helping people out is awesome, and that's how you increase your force in the world. So all of these are examples of unbalanced forces. If you're playing tug of war and somebody's winning, right, we got 50 newtons going this way, 30 going this way. What's our net force? 50 minus 30 gives me 20 newtons going to the left. Okay. Here, if I got 16 newtons going up and 25 newtons going down, right, opposite directions, do I add or subtract? I subtract. 25 minus 16 gives me 9 newtons, and down is bigger, so we're going down. Here, I got 2 4 newtons going to the right, 1 3 newton going to the left. I add these two together first. 4 plus 4 is 8, and then 8 minus 3 gives me 5 newtons going to the left, or to the right, because right is bigger. And what about this one? I got 100 newtons going straight up. Oh, I can't see the bottom of that there. You get the idea, right? It's very simple, okay? I don't think I wrote this down anywhere, but write this down, okay? If the forces are in opposite directions, you subtract. If the forces are in the same direction, you add them. All right. Okay, so which one of these, stop for a second and read these. Which one of these are an unbalanced force? A train traveling at 30 meters per second, a car stopped at a red light, a bicycle making a left turn, or a sprinter taking off at the beginning of the race. Which ones are unbalanced? Did you say the bicycle and the sprinter? Good job. The bicycle is unbalanced because it's turning, so even though it's not changing speed, it's changing direction. And remember, acceleration is unbalanced, period. If it's accelerating, it's unbalanced, okay? All right, write this down. The word equilibrium. If you've never heard this word before, sometimes it's helpful to break words down into smaller bits. Look at the first couple letters there. They look almost identical to the word equal, because that's what equilibrium means. It means two things are equal, all right? So this is just really another way of saying a balanced force. Equilibrium is a state in which there is no change in motion. Meaning, if the object is at rest, it doesn't change, it stays at rest. And if the object is moving, it keeps moving. It's in equilibrium because it's balanced. It's really just another way of saying the same thing, okay? Which means it's either at rest or at a constant velocity, and the total force on the object equals 0. Why? Because it's balanced. Go back, check your notes. These are the exact same thing. So if you see the word equilibrium, it just means that it's a balanced force. like a tightrope walker. Again, balance forces, there's no change in motion. They're equal and opposite. Whereas unbalanced forces, we're going to have motion towards the right because we have 10 newtons of force here and only 5 newtons of force here. So we're going to be going 5 newtons to the right. All right, so the first thing I told you is that this law is called Newton's law of inertia. All right, but we're talking about balanced and unbalanced forces. Newton's first law is called the law of inertia. All right, what is inertia? It's kind of a strange definition, but inertia is the resistance of an object to change its motion. Inertia is how good an object is at staying in rest or how good an object is at staying in motion. If an object has a lot of inertia and it's at rest, it takes a lot of force to start moving it. And if an object has a lot of inertia and it's moving, well, it takes a lot of force to stop it from moving, okay? The easy thing about inertia is there's only one thing that determines how much inertia something has, and that is its mass. All we care about is the object's mass. If you don't remember the word mass from chemistry or biology, mass is how much of something there is. Technically, it's how many atoms make something up, but if something has more mass, the easiest way to think about it on Earth is it has more weight. They're not exactly the same. We'll talk about that in the future. But if it makes it easy to think about it now, mass is kind of like weight. Okay, it's how much of something there is. All right? Simply put, the bigger the object, the more inertia it has. That's it, right? Think about two things. Think about an elephant and an ant. If an elephant is at rest, it's very difficult to change its motion, right? You need a lot of force to push the elephant. Okay? The ant, you don't. You need very small force to be able to move the ant, right? Not that that's nice. Similarly, if the elephant is moving, if it's in motion and you wanted to stop it, that would make it very difficult, right? Whereas the ant, if an ant is moving and you want to stop it, it's like, boop, just a little bit of force, okay? And that is solely determined. The only thing we care about with inertia is its mass. Underline this. This always pops up. So let's make sure you got it. Which one of these two has a greater inertia? A speeding bullet or a stationary train? Which one of these has more inertia? I know this one's tricky. Because think about this, you would say which one is harder to stop? And a lot of people want to say that the speeding bullet is much harder to stop. And that's true, but that's for a different reason. Okay? The one with the greater inertia is the train. Why? It's bigger. It's not moving. Doesn't matter. Think about it this way. Okay? If the bullet was not moving, which one would be easier to move? Well, the bullet's easier. It has less inertia. Similarly, imagine that the bullet and the train were moving at the same speed, right? Which one would be harder to stop? Well, the train would be much harder to stop, okay? Why? It has more inertia. Let's try again. Which one of these has more inertia? An 18-wheeler traveling at 20 meters per second or a Lambo traveling, that's what I call Lamborghinis, a Lambo traveling at 80 meters per second. Did I say 80 for both? The first one is obviously 20. I may have misread that. Which one of these has more inertia? Hopefully you picked up. It's the bigger one. Which one's bigger? The 18-wheeler. Okay? So go back. You don't have to write down these practice problems, but make sure you write down the notes and then use them to complete the DOL. If you have the notes, today should be a piece of cake. All right? Come find me if you have any questions. Have a great day.